Hi class. In this video we'll use torque to help us solve a statics problem in which a body is at equilibrium. So if we remind ourselves what equilibrium means, it means that the translational acceleration is 0 and the angular acceleration is also 0. Um, And if you look at this picture of this person doing a push-up, we assume that this person is in equilibrium at this point. So they're just holding there. And we want to know what F reaction is and what FP is, given that we know what the person's weight is. And here weight is just force of gravity, which is mass times the acceleration of gravity, which is about 500 newtons. Okay. So what we would know so far about statics problems is that you can go ahead and draw a free body diagram for this and write the equilibrium condition. So just to review real quick, free body diagram right here, you would have a force of gravity that points this way. And then you would have a force reaction and a force FP. So I'm going to call, so FP is right there and the force of the reaction is right there. And you know that just looking at this graph, you will know intuitively that when you add these two forces, they have to be the same as the gravitational force. So let's go ahead and write this out. So the sum of all the forces must be equal to 0. Then that means that Fp plus Fr plus Fg equals to 0. And at this point, you have to decide what coordinate system you're going to choose. In this, there's a very natural choice here. You say that this is the x plus axis, the y axis up there, and now you can, and then the next step was going to do the free body diagram, and then you look at the free body diagram, there are no forces acting on x. So there's only a y equation, and we get rid of these vectors here, you will find that Fp plus Fr minus the gravitational force, or the weight, must be equal to 0. And at this point, you probably realize you ran into a problem, right? You have, so let's review what we have here. So we have a force of gravity, great. We don't have force, the reaction force, and we don't have force P. All right. So you can't solve this equation. We have two unknowns. And by now you should know, if we have two unknowns, we need at least two equations to solve for the variables we need. Okay. So what we're going to do is we're going to use an additional equilibrium condition. This body is free to rotate, and when that happens, for equilibrium to be achieved, all of the torques must also be set to 0. Okay. So if torque, if a body that can rotate is in equilibrium, then the total sum of all its forces must be equal to 0, and the sum of all the torques must be equal to 0. Okay, good. So now we have three forces, which means we have potentially three torques. So torque P due to force P plus torque reaction due to the reaction force plus a torque due to gravity, G, equals to 0. Okay, so now we have to get rid of these arrows. Torque is a little more involved than forces, because when we decided x and y for a coordinate for forces, it did not matter where we put our 0, which means it did not matter where in our coordinate system the 0 line was. But here it does matter. So let's erase this real quick and rewrite our coordinate system in an appropriate position. I would always almost pick so when you set a 0 in your coordinate system, you could make your life very hard or very difficult. You could put the 0 axis anywhere. So I could put the 0 axis here. I could put the 0 axis here. It does not matter where I put this axis. But a good rule of thumb is that you take one of the variables you don't know, and that's where you put your 0x, y axis. And you'll see it in a moment what I mean by that. So let's pick this force P right here. I'm going to set this point as my 0, which means that this is my y coordinate, and then this is my x coordinate. Now let's remind ourselves what torque was. So if you look at just an individual torque, it's an R cross F. And what this means here is that let's write the torque due to gravity. So the torque due to gravity is due to this one, which means that I draw a line from my 0 point all the way to where the force acts. Now, gravity always acts on the center of mass on an object, and the center of mass was already given to us. It's right here, right? So now we have this, I'm going to call this RG. That's that is the distance in which the gravitational force acts from my 0 coordinate point. Okay, that's R of G. And remember, what this cross right here means is that, so torque of G, R of G, F of G, what this cross product means, it means that whatever distance I pick here from the 0 point to where it acts on an object, take the whatever amount of this vector that is perfectly perpendicular to it. Now, weight is already perfectly perpendicular to it, so you don't have to do anything. You can just multiply them together. And another thing is that another way of looking at this is it's also the sine. So this torque is also Rg times Fg times the sine of the angle between these two quantities, right? So what happens is this angle here is 90 degrees, right? So if this is 90 degrees, then sine of 90 degrees, that's just 1, and so you're just left with this, right? So you know that the torque, the amount of torque is Rg and Fg. What you don't know is what you're going, if it's going to be a positive or a negative torque, because again, you still have these arrows. Good. So that was the explanation for what we're going to do to these 3 quantities, right? So this is one example of 3 quantities we're going to do. Another thing I'm going to define here is our reaction. So our reaction is from the 0 line all the way up here. Now I ask you, what is R? R again is the distance or the displacement from the point in which you decide your coordinate is 0, 0 to where the force is applied. So Fp is applied right at 0. So what do you suppose our P is going to be? And hopefully you see that it will be 0, meaning that the force of P is being applied at the point where we decided that it was going to be our coordinates 0, 0. So there will be, again, if R is 0 here, then the torque is 0 there. And this is what I meant by you can pick a coordinate system that's going to make your life easy, or you can pick a coordinate system that's going to make your life difficult. If you pick a 0, 0 point where you don't know one of the forces, it just so happens that this force will go away because R is 0. So let's finish this. Right. So let me go ahead and write out. So from this line right here, the torque at P, that's going to be 0. Great. Plus torque due to the reaction force is right here. It's R reaction force cross with the force of reaction. Good. Plus the gravitational displacement vector multiplied by the force of gravity. This all needs to be 0. And the last thing, to get rid of these arrows here, we already know that both of these vectors are perfectly perpendicular. There's a 90-degree angle there. There is a 90-degree angle there. So all of these signs here will go away. So they're all going to be these multiplied by these without the arrows. But now we have to decide on positive or negatives. So we need to get rid of the vector quantities and just be able to write them algebraically. Which that means is, remember, any force that makes this person want to rotate this way is going to be positive, and every force that's going to make the person rotate this way will be negative. If you look at this weight here, just imagine this person can rotate around this point, at point 0. This force is going to want to rotate it the negative way. So torque here, so this quantity here will be negative. And if you look at the reaction, this one is trying to push the person this way, to rotate this way, according to positive, meaning that this is positive. All right. So far, so good. I think we got everything from the image to be able to solve this problem. So we are faced with this system of equations, meaning that, so let me finalize the torque calculation here. So these two, this will be positive, right? So this is R, F, R, plus, minus. Remember, we decided that was going to be minus. R, G, F, G equals 0. So now what we have here is we have two equations. We have equation number 1 here and equation number 2 here. What you may know is that, what you may already notice is that we do not need to solve for one variable in one equation and plug it into the other, because if you inspect this equation right here, let's look at what we have and what we don't have. R sub R and R sub G we have, remember. R sub G is in the picture here, it tells you. So let's write it out right what it is. So R of G here, if you look at the picture, it's from here to here is 0.9, and R sub R here is from here to here, and it says in the picture is 1.5 meters. So both of these we have. Okay, good. Both of these we have. Force of gravity, remember, that was 50 newtons, or 500 newtons. So if 50 kilograms, you multiply by around 10 meters per second squared, you get the 500 newtons. So the only thing you don't have here is this. So you can solve for F sub r. Once you solve for F sub r, force of reaction goes into here. Then you have a force of friction, force of gravity. You have force of reaction, and you can solve for force P. So if you would like to practice how to do these things, go ahead and see if you can do that. Again, remember that F R sub G was the 0.9 and R sub R is 1.5. Okay, so let me go ahead and solve this for you. So when you solve this equation here for F sub R, the reaction force equals to the distance from where the gravitational force acts from the zero to the distance where the reaction force acts from the zero, multiplied by the force of gravity. And when you put in some numbers here, you get 0.9, which is 0.9 meters, 1.5 meters, times 50 kilograms, times about 10 meters per second squared. Let's just round it, because you get a nice number. If you notice here, let's check our units. Meter goes away. So as long as these two units, and note, I could have given you feet here, and the feet just the feet will go away here. So as long as these, whenever you have a reciprocal or a division of two like units, then as long as the two units are the same, you don't have to convert, and we've seen this over and over again. So this is 0.9 divided by 1.5, you multiply by 50 kilograms times 10 meters per second squared. A kilogram meter per second square is a Newton, so everything checks out. So this will turn out to be 300 Newtons. And then from now, for the FP becomes very simple. So FP, it will be 500 Newtons minus 300. So basically we go to this equation right here and we solve that equation, okay? So if you go ahead and then use the force part of our equilibrium, we find that force P equals to force of gravity minus force of reaction, which if we found, force of gravity is about 500 newtons, and we already did that. It's so this 500 newtons here is this 500 times 10 right there. It's the same. Minus 300 Newton, and what you get here is the remainder. So it's 200 newtons. Okay, so that is how you use torques to solve a problem like this. Okay, so just to review the entire problem, if you were given this problem, and let me clean this up so you remember what you were faced with at the beginning. Oh, I can't do that. All right, never mind. So if you look at this whole this image here, and you were just asked find FP and find F reaction, and you were not told that you need to use torque, you're going to run into this problem. So all of you have experience with this, where you will write sum of all forces equal to 0, you'll do the free body diagram, you get this done, you get to this point, you're not going to be able to solve the problem. And at this point is where you have to ask yourself, is this object allowed to rotate? In this case, yes, it is allowed to rotate, and using the additional condition for equilibrium allows you to solve this problem in the way that we have, because then you are going to have two equations here for two variables, and then the rest is just math. All right. So okay, so this concludes the example I wanted to do for torque. I should have one more example on Wednesday for all of you. Have a good day, and I'll speak to you all soon.